Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body begin to release the weight of the day. If this gentle journey is already starting to slow your thoughts, consider subscribing now, so these stories can keep finding you, night after night. Now, let the relaxation settle into your breathing. Beneath the surface, there's a world no one has ever fully seen. A territory larger than all the continents combined, submerged in absolute darkness, where pressure can crush metal like paper, and yet, life found a way. The deepest point in the ocean has been visited fewer times than the surface of the moon. A place on our own planet, and we've reached it with more difficulty than we've reached another world. And the more we observe what exists down there, the more astonishing it becomes. The ocean most people picture, that blue strip visible from the shore, that surface glittering in the sun, represents a small portion of everything that exists. Below the first 200 meters of depth, a region begins that covers more than 60% of the total surface of planet Earth. It's a territory without parallel, and yet it remains the least explored environment anywhere in this world. This division isn't just geographical. The first 200 meters, called the photic zone, is where sunlight can penetrate with enough intensity to sustain photosynthesis. Below that, conditions change so radically that scientists treat the layers that follow as completely different environments, almost like separate planets within the same planet. The same Earth, but an entirely different world. And what makes this even more fascinating is that for most of human history, this vast territory simply didn't exist for us. There was no way to see it, reach it, or understand it. Serious exploration of the deep began less than 200 years ago, a blink of an eye in geological terms. All of our curiosity about the abyss is, in fact, very recent. The deep ocean isn't a uniform place. It's organized in layers, and each one has completely distinct physical, chemical, and biological characteristics. The mesopelagic zone runs from 200 to 1,000 meters. Light still reaches here, but so faintly it can't support photosynthesis, just a blue twilight that slowly fades away, like a last memory of the sun. The bathypelagic zone begins there and extends to 4,000 meters, total darkness, increasing pressure, temperatures close to zero. Below that, the abyssopelagic zone covers the great ocean floors, between 4,000 and 6,000 meters. And in the trenches, the deepest cracks in the oceanic crust, there's the Hadal zone, which starts at 6,000 meters and can exceed 11,000. Each of these zones filters organisms based on what they can withstand. It's not that life becomes scarcer as depth increases, it's that it becomes progressively more specialized and, in many cases, unrecognizable to anyone familiar with what exists at the surface. As if pressure and darkness were patient sculptors, shaping each form of life over millions of years. There's a comparison that helps put all of this in perspective. If you climbed Mount Everest upside down, starting from sea level, you'd still need to dig an additional 2,000 meters to reach the ocean's deepest point. The Mariana Trench, in the Pacific, reaches 10,935 meters at its lowest point, a region called Challenger Deep. That depth was first measured with reasonable precision in 1875, during the expedition of the HMS Challenger, the first oceanographic research vessel in history. At the time, scientists used weighted cables to measure depth, a laborious method that took hours for a single measurement. The image of those sailors throwing cables into an abyss they couldn't see says a great deal about how much the deep ocean has always challenged humanity's ability to understand it. Today, with sonar and robotic vehicles, measurements are far more precise. But Challenger Deep still holds surprises, and each recent expedition finds details that previous ones couldn't record. It seems that the closer we get, the deeper the abyss retreats. One of the first questions that comes up when studying the deep ocean is, why is it so unknown if Earth is mostly covered by water? The answer has to do with the difference between being on top of something and being able to explore it. The ocean's surface has been sailed for millennia. But going down is a completely different problem. Water is incompressible, and that means as depth increases, the pressure built up by the water column grows in a linear and relentless way. For every 10 meters of depth, pressure increases by approximately 1 atmosphere. At 11,000 meters, the pressure is over 1,000 atmospheres, the equivalent of having 50 commercial aircraft stacked on every square centimeter of your body. Building equipment that can withstand that without imploding required engineering that only became viable in the second half of the 20th century. And even today, vehicles capable of reaching the deepest zones can be counted on one hand, which explains why certain parts of the ocean floor have been visited fewer times than the surface of the Moon. We have more detailed maps of other worlds than of our own seafloor. And there's one detail that changes everything when you start to understand the deep ocean. For centuries, science believed that below a certain depth, life would simply be impossible. For centuries, there was a widely held belief in science that below a certain depth, somewhere around 550 meters, life would be impossible. This idea had a name, the azoic theory, proposed by naturalist Edward Forbes in 1843. The logic seemed solid. Without light, with crushing pressure and temperatures near freezing, no known organism could survive. Forbes reached this conclusion after dredging the Mediterranean Sea and noticing that the deeper he went, the fewer organisms he found. The problem is that his equipment didn't come close to reaching the real depths, and the Mediterranean has particular characteristics that make it less biodiverse in its deeper layers than the great oceans. It was an honest conclusion, based on the available data, just incomplete. The azoic theory began to fall apart in the 19th century, when submarine telegraph cables were pulled up for maintenance covered in organisms living at more than 1800 meters. Every time technology allowed a deeper look, life was there, adapted in ways no one had predicted. That story is a gentle reminder that the boundaries of the impossible in biology tend to be revised by nature itself. The ocean floor isn't flat. That's one of the first surprises for anyone who begins to study the subject more carefully. There's a topography down there as complex as any on land, with mountains, plains, volcanoes, canyons, and trenches that rival any continental landscape. The abyss has relief. It has shape. It has its own geography, invisible but real. The Mid-Atlantic Ridge, for example, is an underwater mountain range that runs through the Atlantic from north to south for more than 16,000 kilometers, the longest mountain range on the planet, completely submerged. In the Pacific, there are abyssal plains so vast and flat they seem impossible, the result of centuries of fine sedimentation slowly filling in any irregularity in the terrain, like a very slow, very patient snow. The ocean trenches, in turn, are formed where one tectonic plate dives beneath another, a process called subduction. They're not just the deepest points of the ocean, they're regions of intense geological activity, where the seafloor itself is being constantly recycled by plate dynamics. What exists in those trenches, in terms of life and minerals, is still largely unknown. The word abyssal comes from Greek and means bottomless, and there's something revealing in that etymology. For a long time, the oceanic abyss was treated as a non-place, vast, inaccessible, and presumably empty. That perception shaped not only science, but also the way entire societies ignored the deep ocean as an object of concern or care. Today we know that the abyssal plains, lying between 3,000 and 6,000 meters of depth, cover about 54% of the ocean floor. They are the most extensive environments in Earth's biosphere. And contrary to what the word abyss suggests, they're not empty, they shelter communities of organisms adapted to darkness, cold, and the scarcity of food that arrives from above in the form of organic particles. What's interesting is that these plains also function as geological archives. The sediments that accumulate there over millions of years preserve records of climate changes, volcanic events, and even meteorite impacts, information that scientists are learning to read with growing precision. The ocean floor is, among other things, a memory of the planet. What almost no one realizes is that the abyss isn't static, it moves, shifts, breathes in its own way. There's a detail about the deep ocean that rarely appears in general descriptions: it's not completely still. The image of the abyss as a motionless and eternal place is partly misleading. The ocean floor is subject to currents, landslides, sediment storms, and disturbances generated by earthquakes and underwater volcanic eruptions. These events can reshape the seafloor significantly in a matter of hours. Submarine landslides have moved volumes of sediment larger than any terrestrial avalanche ever recorded. In 1929, an earthquake off the Canadian coast triggered a landslide that cut submarine telegraph cables in sequence, and from the order in which the cables were severed, scientists were able to estimate the speed of the sediment flow, somewhere between 60 and 100 kilometers per hour, at more than 3,000 meters of depth. This dynamism has very concrete practical implications. Much of the world's global communications infrastructure, fiber optic cables that carry the majority of the world's internet traffic, is laid on the ocean floor. Understanding the geology of that environment isn't just a scientific matter, it's also a matter of engineering, of safety, of connection between continents. One of the most fascinating questions in deep ocean physics has to do with oxygen, or its absence in certain regions. The deep ocean in general does have dissolved oxygen, brought by cold water currents sinking from the poles. But there are intermediate zones, between 200 and 1,000 meters, where oxygen reaches minimums so extreme they would be lethal to most animals. Invisible zones, but real. A natural question that comes up when studying the deep ocean is, when did it form? The answer is more complicated than it seems, because the ocean floor that exists today isn't the same as it was 200 million years ago. The seafloor is in constant renewal, and is actually much younger than the continents. The oldest rocks found on the ocean floor are about 200 million years old. For comparison, some continental rocks are more than 4 billion years old. The reason is the subduction process. The seafloor is continuously created at mid-ocean ridges, where magma rises and solidifies, and destroyed at trenches, where it dives back into Earth's mantle. It's a slow but unceasing cycle that completely recycles the oceanic crust every few hundred million years. This means the abyss that exists today is, in geological terms, relatively recent. And the organisms that inhabit it evolved in this constantly changing environment, which adds a layer of wonder to questions about how life adapts to extreme conditions over time. Everything below us is younger than it looks. There's something deeply counterintuitive about the deep ocean that's worth understanding before we go deeper. Despite all its vastness, it's an environment of extreme scarcity. Life in the abyss is, for the most part, a story of adaptation to hunger. The energy that sustains almost all life at the surface comes from the sun, via photosynthesis. In the abyss, the sun doesn't exist. The only continuous food source for most deep organisms is what sinks from the surface, fragments of dead organisms, feces, organic particles. This material is filtered through the intermediate layers during its descent, and what reaches the bottom is a tiny fraction of what existed above. It's estimated that only 1 to 3% of the organic production at the ocean's surface reaches the abyssal plains. This explains why the organisms that live there have developed such radical survival strategies, extremely slow metabolisms, the ability to go without food for months or years, and the capacity to take advantage of any available energy source, including some that challenged all known biology when they were first discovered. This starts to get more interesting when you understand what pressure actually does to matter in the depths. Pressure is probably the most often cited characteristic when talking about the deep ocean, but what it actually does to matter goes far beyond the intuitive idea of crushing. The pressure in the deep doesn't just act on the outside of objects, it penetrates and alters molecular structures, shifts melting and boiling points, and transforms the way chemical substances react with each other. Water behaves differently under extreme pressure. Under normal conditions, liquid water becomes ice below 0 degrees. But under very high pressures, that freezing point shifts. At the bottom of ocean trenches, water can remain liquid even at temperatures slightly below 0, because pressure prevents the formation of ice crystals. A small detail that has enormous implications for any organism living there. For the proteins and cell membranes of living things, pressure is a serious problem. It tends to compress cell membranes and distort the shape of proteins, interfering with biochemical reactions. Deep-sea organisms have developed specific molecular adaptations to keep their cells functioning normally under these conditions, and understanding these adaptations has produced interesting discoveries for biotechnology. Life solved a problem that human engineering is still studying. The temperature of the deep ocean is surprisingly uniform and surprisingly cold. While the ocean's surface can range between -2 and over 30 degrees Celsius depending on latitude and season, the Great Abyssal Plains stay between 1 and 4 degrees Celsius most of the time. This thermal stability has existed for millions of years and has profoundly shaped every organism that lives there. This cold, dense water in the depths didn't get there by chance. It originally formed in polar regions, especially in the North Atlantic and around Antarctica, where surface cooling increases water density, causing it to sink and flow slowly toward the bottom of tropical oceans. This process takes centuries. The water sitting on the floor of the Pacific today may have sunk at the poles 500 or 1,000 years ago. There's a notable exception to that cold uniformity, the regions near hydrothermal vents, where superheated water emerges from the seafloor through geothermal chimneys. In those spots, temperatures can exceed 400 degrees Celsius without the water boiling, because the pressure is too high to allow a change of state. It's one of the most extreme environments on the planet, and yet it hosts life that is dense and surprisingly diverse. The absence of light in the deep ocean isn't just an environmental detail, it's an evolutionary force of enormous power. Below 1,000 meters, no sunlight penetrates. The environment is one of absolute, permanent darkness, something humans can barely imagine accurately, because even in dark environments at the surface there's always some residual radiation, some distant reflection. This darkness eliminates vision based on reflected light as a primary survival strategy. Eyes like those of surface fish and mammals would be useless there, and indeed, many abyssal species are blind or have very reduced eyes. But what's interesting is that the absence of sunlight doesn't mean the absence of light in general. Bioluminescence, the production of light by the organisms themselves, is present in an estimated 76% of species inhabiting the deep ocean. The eye, in this environment, didn't disappear, it reinvented itself. Some abyssal species have enormous, hypersensitive eyes capable of detecting the faintest spark of bioluminescence in the darkness. Others developed photoreceptors that pick up wavelengths that don't exist in sunlight but are present in biological light. Darkness didn't eliminate vision, it transformed it into something completely different, perhaps more sophisticated. And there's a detail that changes everything when you think of the deep ocean as a silent place, because it isn't. The deep ocean has a sound, and it's richer and more complex than anyone would imagine. Water is a much more efficient conductor of sound than air. Sound travels through it about 4.3 times faster, and can cover enormous distances with minimal energy loss. The abyss is not silent. It resonates. There's a specific layer in the ocean, at approximately 600 to 900 meters of depth, where temperature and pressure conditions create a natural acoustic channel called SOFAR, a name that comes from sound fixing and ranging channel. In this layer, sound waves become trapped and propagate horizontally for thousands of kilometers without dispersing. During World War II, the military used this channel to locate downed airmen. The pilot would detonate a small explosive charge picked up by hydrophones on distant continents, allowing their position to be triangulated. Blue whales and other cetacean species have been using this same channel for far longer than humans. Their low-frequency songs travel through the SOFAR channel and can be detected more than 3,000 kilometers away. The deep ocean is, in acoustic terms, a continental communication environment, something that completely contrasts with the image of absolute silence usually associated with the abyss. The salinity of the deep ocean seems simple but hides unexpected complexity. In general, ocean water has an average salinity of around 35 grams of salt per liter. In the deep, that concentration tends to be slightly higher and more stable than at the surface. But there are points on the ocean floor where salinity reaches values that defy any expectation. At the bottom of the Red Sea and in certain regions of the Mediterranean and the Gulf of Mexico, there are accumulations of brine so concentrated that they form lakes on the ocean floor, lakes within the sea, with a distinct surface and their own waves. The brine water is so dense that submarines float on it as if it were a solid bottom, and most marine organisms die upon contact with it. Lakes inside the sea. A surface within the water. And in those brine lakes, there is life. Extremophile microbes have been found thriving in conditions that would be lethal to virtually any other organism. This kind of discovery continues to be relevant not just for marine biology, but for discussions about the possibility of life on other planets with equally extreme conditions. If life thrives here, where else might it thrive? What seems simple, isn't, and that applies to almost everything in the deep ocean, including ice that burns. There's a physical phenomenon in the deep ocean with implications for both geology and global climate, the formation of methane hydrates, also known as burning ice. These structures form when methane molecules become trapped inside a crystalline network of water molecules, under conditions of high pressure and low temperature, exactly the conditions found in seafloor sediments. Methane hydrate deposits on the ocean floor are immense. Conservative estimates suggest they contain more carbon than all known reserves of oil, gas, and coal combined. A number that's hard to visualize. This methane came mainly from the decomposition of organic matter by bacteria in the sediments, a slow process that has been happening for millions of years, invisible and constant. What makes this especially relevant today is the instability of these structures in the face of warming. If the temperature of the deep ocean rises enough, the hydrates can dissolve and release methane directly into the water column and, eventually, into the atmosphere. Methane is a greenhouse gas with a much greater warming potential than CO in the short term, which makes submarine hydrates an important and still poorly understood element in climate discussions. The chemistry of the deep ocean is affected by a process most people have never heard of, the dissolution of calcium carbonate at extreme depths. At the surface, calcium carbonate, the material that makes up shells, corals, and the skeletons of many marine organisms, is stable in seawater. But from a certain depth onward, called the calcite compensation depth, the pressure and chemical composition of the water change in ways that cause the carbonate to begin dissolving. This has a direct consequence for what sinks and what gets preserved on the seafloor. Organisms with calcareous shells that die at the surface and begin their descent will gradually dissolve along the way. Below the calcite compensation depth, virtually nothing calcareous arrives intact at the bottom. What accumulates on the deepest abyssal plains is mainly clay and silica, the remains of organisms with siliceous skeletons that resist dissolution. This detail has implications for reading sediment records. When scientists analyze sediment cores from the ocean floor to reconstruct past climates, they need to account for what dissolved before reaching there. The record that exists on the floor isn't a faithful copy of what lived at the surface, it's a filtered version, selected by the chemistry of the depths. One of the most fascinating questions in deep ocean physics concerns oxygen, or its absence in certain regions. The deep ocean in general has dissolved oxygen, brought by cold water currents that sink from the poles. But there are intermediate zones, between 200 and 1,000 meters, where oxygen reaches minimums so extreme they would be lethal to most animals. Invisible zones, but real. These are called oxygen minimum zones, and they exist because at that depth, bacterial decomposition of organic matter consumes the available oxygen faster than it's replenished by currents. The irony is that this oxygen scarcity preserves dead organisms that arrive there without enough aerobic bacteria to decompose them. Carcasses and organic particles accumulate and sink more slowly. Some species of fish and invertebrates can exist at the edges of these hypoxic zones, using metabolic strategies that drastically reduce oxygen consumption. Others avoid them entirely, making these zones invisible barriers that fragment populations and shape the distribution of life in the ocean in ways that are still being mapped. The ocean is full of boundaries no eye has ever seen. The deep ocean has color, or rather, it had color before the light disappeared. As sunlight penetrates water, its wavelengths are absorbed progressively. Red disappears first, already within the first few meters. Orange and yellow vanish soon after. Green and blue persist further down, but also fade out before 200 meters. What remains is a blue growing ever darker, shifting into black. This selective absorption has interesting biological consequences. In shallow water, red animals are easily visible, but in the mesopelagic zone, where only faint blue light exists, red appears as black. This turned red coloration into an effective camouflage strategy at that depth, and explains why so many shrimp, octopuses, and fish from the intermediate layers are deep red or orange. They hide in plain sight, using the absence of color as a shield. Below 1,000 meters, where there's no light at all, body color loses its camouflage function. There, other factors take over. Many abyssal species are completely black, making themselves invisible to the bioluminescent flashes of predators, while others are transparent, leaving their internal organs visible like biological lanterns. Evolution works with what's available, and in the abyss, there is no color. There's a physical property of the deep ocean that's rarely mentioned but plays a central role in the functioning of the entire planet: the thermal capacity of water. Water has one of the highest heat-storing capacities of any common substance, and the volume of cold water in the ocean depths represents one of the largest thermal reservoirs on Earth. This reservoir functions as a giant climate buffer. Heat entering the climate system, whether from solar radiation or greenhouse gases, doesn't all go into the atmosphere. A significant portion is absorbed by the ocean and transported to the deep by abyssal currents. Recent estimates indicate that the ocean has absorbed more than 90% of the excess heat generated by global warming since the 19th century. This has two sides worth contemplating. On one hand, the deep ocean has buffered atmospheric warming. Without it, air temperatures would have risen much more by now. On the other hand, the heat stored in the deep hasn't disappeared. It's there, influencing ocean circulation, the melting of sea ice, and the behavior of climate phenomena. The abyss isn't a passive repository, it's an active participant in the global climate. This starts to get more interesting when you realize that no one yet knows how many species live in the deep. When the first marine biologists began cataloging life in the deep ocean, they expected to find simple organisms, perhaps resistant microbes, and not much else. What they found, over decades of expeditions, was a diversity that still hasn't been fully catalogued. Current estimates suggest that between 500,000 and 10 million species inhabit the deep ocean, and most still have no name. That wide range in the estimate isn't scientific imprecision, it's an honest reflection of how much is still unknown. Every expedition that descends with better equipment than the one before returns with new species. In some regions of the abyssal plains, more than 50% of the organisms collected in a single sediment sample are species that have never been described by science. What this means in practice is extraordinary. We are actively cataloging one of the planet's largest biomes in real time. Unlike tropical forests, where new species are found but the general environment is well understood, the deep ocean still holds surprises, not just in terms of individual species, but in terms of entire ecosystems that no one knew existed. Every dive is potentially a discovery. Bioluminescence is so common in the deep ocean that it would be more accurate to describe it as the norm, not the exception. It's estimated that about 76% of all organisms living between 200 and 1,000 meters of depth produce some form of biological light. In the deeper layers, that proportion may be even higher among certain categories of animals. The abyss glows, in its own way. The mechanism behind bioluminescence involves a chemical reaction between a molecule called luciferin and an enzyme called luciferase, in the presence of oxygen. This reaction releases energy in the form of photons of light, with surprisingly high efficiency, since almost all the energy from the reaction converts to light, with minimal heat. That's why bioluminescence is called cold light. What makes this even more fascinating is that bioluminescence evolved independently at least 40 times in different lineages of marine organisms. That means it's not inherited from a single common ancestor, it's a solution that evolution discovered repeatedly because it works extremely well in that specific environment. Few biological traits have such a diverse evolutionary history. In the deep ocean, producing light is almost inevitable. Among all the creatures of the deep ocean, the black dragonfish deserves special attention, not for its size, but for a visual ability that has no known equivalent in the animal kingdom. This fish, which lives between 200 and 1,000 meters of depth, can produce and see red light, a wavelength that, at that depth, is completely invisible to any other organism. Most deep-sea animals can only see blue and green light, which are the wavelengths of the most common bioluminescence. The black dragonfish uses this to its advantage. It projects a beam of red light, essentially an invisible spotlight, to illuminate its prey without being detected. It's the biological equivalent of an infrared night vision device, developed by evolution independently of any human engineering. The origin of this ability is equally curious. The photoreceptors of the black dragonfish contain modified chlorophyll, yes, the same pigment that plants use in photosynthesis, adapted to function as a red light detector. It's an example of how evolution reuses solutions from completely different contexts to solve new problems. Nature doesn't invent from scratch, it reimagines what already exists. What almost no one realizes is that some of the most radical survival strategies in the deep ocean involve reproduction. The Dumbo octopus, whose scientific name is Grimpotuthis, is one of the most unusual animals in the deep ocean, and one that best illustrates how evolution can produce radically different forms when the environment demands it. It lives between 3,000 and 7,000 meters of depth and moves using two ear-shaped structures above its eyes, hence the nickname inspired by the flying elephant from the animated film. Unlike shallow water octopuses, which have ink sacs to escape predators, the Dumbo doesn't have that mechanism. In its environment, visibility is so low that ink jets would be useless. Instead, it developed an escape behavior that involves pulling in its tentacles, folding its body, and swimming quickly using its ears, a completely different solution to the same survival problem. The Dumbo also has one of the most unusual reproductive cycles among cephalopods. Females carry eggs at different stages of development simultaneously, a state called continuous reproduction, which allows them to deposit mature eggs as soon as they find a suitable substrate, without depending on a specific breeding season. In an environment where encounters between individuals are rare, this strategy makes considerable evolutionary sense. The concept of marine snow is one of the most important for understanding how life is sustained in the deep ocean, and the name is more accurate than it seems. Marine snow consists of a continuous rain of organic particles falling from the ocean surface toward the bottom, fragments of dead algae, zooplankton feces, decomposing carcasses, mucus from filter-feeding organisms, and aggregated bacteria. A snow that never stops. These particles descend slowly, some take weeks to travel 1,000 meters, and are colonized by bacteria as they fall, which begin decomposing them before they reach the bottom. So the deeper they go, the less nutritional energy remains in the material that arrives. What reaches the abyssal plains is an impoverished fraction of what existed at the surface. But there are seasonal variations in this flow that profoundly affect seafloor ecosystems. When a phytoplankton bloom occurs at the surface, an explosive growth of microscopic algae, usually in spring, a much larger amount of organic material sinks in concentrated pulses. Bottom organisms respond to these pulses actively, entire communities increase their metabolic activity, invertebrate populations grow rapidly. The abyss has a seasonality of its own, with a delay of weeks or months relative to the surface. There's a category of event that represents an extraordinary feast for the deep ocean ecosystem: the fall of a dead whale. When a whale dies and sinks, its body, which can weigh tens of tons, represents an input of concentrated organic matter equivalent to centuries of normal marine snow arriving all at once in a single spot. This phenomenon has its own name in marine biology: whale fall. And it isn't just a feeding event, it's a temporary ecosystem with its own ecological succession, passing through distinct phases over decades. In the first phase, deep-sea fish and sharks consume the soft tissue within months. In the second, invertebrates like polychaetes and crustaceans colonize the skeleton and extract the remaining nutrients. In the third phase, the longest, anaerobic bacteria penetrate the fat-rich bones and produce hydrogen sulfide, creating chemical conditions that sustain a chemosynthetic community. Each whale fall can sustain local ecosystems for decades. And it was recently discovered that some species found exclusively at these sites also appear near hydrothermal vents, leading to the hypothesis that whale falls may function as evolutionary stepping stones, connecting isolated populations across millions of years. The death of a whale is the birth of an ecosystem. Deep-sea fish often have physical features that look exaggerated at first glance: disproportionately large jaws, teeth that don't fit inside a closed mouth, bodies that seem assembled from parts of different animals. These features aren't aberrations, they're precise solutions to the central problem of life in the abyss, which is finding and capturing food in an environment where it's extremely scarce. The viper fish, for example, has teeth so long they have to stay outside the mouth even when it's closed. This isn't a design flaw. Those teeth work as a trap that maximizes the chance of holding onto any prey that comes into contact with them. In an environment where meals can be separated by days or weeks, losing a prey item would be a significant evolutionary cost. The black swallower goes even further. Its stomach is expandable to the point of accommodating prey larger than the predator itself. It's not a metaphor. There are photographic records of specimens found dead at the surface with larger fish decomposing inside their stomachs, having sunk because of the weight of the prey. That level of storage capacity makes perfect sense in an environment where feeding opportunities are rare and must be taken full advantage of. And this is where things get strange. In the Mariana Trench, at more than 10,000 meters of depth, there are crustaceans that don't just survive, but thrive. One of the most unsettling discoveries in deep-sea biology was made not during a major scientific expedition, but almost accidentally during the retrieval of submarine cables in the 19th century, living organisms at depths that should have been impossible. Since then, with each technological advance, the depth limit at which life is found has been pushed further down, until reaching the deepest point of all. In the Mariana Trench, at more than 10,000 meters of depth, amphipods were found, crustaceans resembling shrimp, that don't just survive under pressure of more than 1,000 atmospheres, they thrive. Biochemical analyses revealed that their cell membranes contain compounds called polyunsaturated fatty acids at much higher concentrations than normal, an adaptation that keeps membranes fluid and functional even under extreme pressure. What these organisms reveal is that life has no depth limit determined by pressure itself. It has a limit determined by its ability to adapt its biochemistry to new pressures. And since evolution operates precisely on that biochemical variability, the result is that life has found ways to exist at virtually every point in the deep ocean where there is liquid water and some source of energy. The metabolism of deep-sea organisms operates at a speed that defies comparison with the surface world. In environments of low temperature, high pressure, and food scarcity, metabolic processes that take hours in surface animals can take days or weeks in the deep. Some species of abyssal fish have metabolic rates so low they consume oxygen at a fraction of 1% of what an equivalent fish would at the surface. This metabolic slowness has a direct counterpart, longevity. Many deep-sea organisms live extraordinarily longer than their shallow water relatives. The Greenland shark, which inhabits the cold, deep waters of the North Atlantic, was recently identified as the longest-lived vertebrate known. Specimens have been radiocarbon dated at ages between 272 and 512 years. An animal that may have been born before the Industrial Revolution could still be alive today. This extreme longevity has conservation implications that are rarely discussed. Species with long lifespans and slow metabolisms also have late sexual maturity and slow reproduction. A Greenland shark takes about 150 years to reach sexual maturity. Any pressure on their populations takes decades or centuries to show up as demographic recovery. The time of the abyss is not human time. There's a form of life in the deep ocean that challenges biological categories in ways still being understood. Xenophyrophores. They're unicellular organisms, a single cell, that can reach 20 centimeters in diameter, making them the largest known unicellular organisms on the planet. A cell visible to the naked eye, the size of a human hand. Something that shouldn't exist, and does. They live on the floor of the deepest ocean trenches and build complex structures by incorporating sediment, mineral fragments, and organic particles into their surface, creating a kind of external skeleton that gives them shape and protection. These structures, called tests, can have elaborate forms and are built by the cell itself in ways that aren't yet fully understood. What makes xenophyrophores even more interesting from an ecological standpoint is that they function as ecosystem engineers. Their structures create microenvironments that other organisms inhabit. Small crustaceans, worms, and foraminifera take shelter among their branches as if they were miniature reefs. In an environment where any physical structure is scarce, xenophyrophores create local complexity where it wouldn't naturally exist. For most of the history of biology, one principle seemed universal and unquestionable: all life on Earth depends, directly or indirectly, on the sun's energy. Plants capture that energy through photosynthesis, herbivores eat the plants, carnivores eat the herbivores, and so on. Even organisms living in dark caves depend on organic matter originally produced by sunlight somewhere in the chain. In 1977, that principle was shaken in a definitive way. An expedition aboard the submersible Alvin, from the Woods Hole Oceanographic Institution, descended to a mid-ocean ridge in the eastern Pacific, at 2,500 meters of depth, expecting to find the cold and relatively empty bottom that models predicted. What they found was one of the most surprising discoveries in 20th century biology: dense, diverse communities of organisms clustered around vents of warm water emerging from the seafloor, hydrothermal vents. There, without any sunlight, were giant tube worms, mussels, shrimp, crabs, and an abundance of life that made no sense within existing models. The energy source wasn't the sun, it was the heat and chemical compounds emerging from the Earth's interior. This discovery didn't just expand the definition of ecosystem, it fundamentally reconfigured what scientists consider possible when thinking about where life can exist. What almost no one realizes is that these sunless ecosystems changed forever the way we understand life, including the possibility of life on other worlds. The mechanism that sustains life at hydrothermal vents is chemosynthesis, a process analogous to photosynthesis, but that uses chemical energy instead of light. At hydrothermal vents, ocean water penetrates cracks in the crust, is heated by magma below, and emerges loaded with reduced compounds, especially hydrogen sulfide. Bacteria and archaea are able to oxidize this compound and use the released energy to build living matter from inorganic chemistry. These bacteria form the base of the local food chain, replacing the role that plants and algae play in sunlit ecosystems. And what makes this system even more elegant is that many of the larger vent animals don't eat the bacteria directly, they host them inside their own tissues. Giant tube worms, which can reach more than 2 meters in length, have no mouth or functional digestive system in adulthood. They get all their nutrition through chemosynthetic bacteria living in a specialized organ called the trophisome. It's one of the most radical symbioses known in biology. An animal that doesn't eat, fed by bacteria living inside it, in an ecosystem that exists without sunlight, at the bottom of the ocean. Each element of that equation seems impossible in isolation, and together, they form one of the most productive and stable ecosystems on the planet. Hydrothermal chimneys have an appearance that blends the volcanic with the architectural. When superheated water emerges from the seafloor and comes into contact with the cold deep ocean water, dissolved minerals precipitate instantly, forming solid structures that grow continuously. Some of these structures, called black smokers when they release dark sulfides, or white smokers when they release barium and silicon compounds, can reach dozens of meters in height. The temperature of the water emerging from these chimneys can exceed 400 degrees Celsius. But it doesn't boil, because the pressure of the deep raises the boiling point well beyond that temperature. This superheated, mineral-laden water forms plumes that rise above the chimneys and disperse through the water column, distributing minerals and chemical compounds over large distances. Hydrothermal chimneys have a limited lifespan, some last decades, others only years, before being clogged by their own mineral deposits or displaced by tectonic activity. When a chimney stops working, the community that depends on it collapses quickly. This dynamism means that species associated with hydrothermal vents need to be able to colonize new chimneys as they emerge, a dispersal problem that biology is still studying. Beyond the hot hydrothermal vents, there's another type of chemosynthetic ecosystem in the deep ocean that works in a completely different way: cold seeps. At these sites, fluids rich in methane and hydrogen sulfide percolate slowly through the seafloor sediments, without the heat associated with volcanic activity. The temperature is the same as the surrounding water, near zero, but the chemistry is equally rich. Cold seep communities use the same basic principle as hydrothermal vents. Chemosynthetic bacteria convert reduced compounds into organic energy, sustaining a food chain independent of sunlight. Mussels, tube worms, crabs, and a variety of polychaete worms are common in these environments, often at extraordinarily high densities compared to the surrounding ocean floor. A particularly interesting detail of cold seeps is that they are geologically stable for much longer than hydrothermal vents. Some persist for thousands or even millions of years in the same location. This allows the development of more complex communities and species with longer life cycles. Some species of tube worms at cold seeps have an estimated lifespan of more than 200 years, making them some of the longest-lived animals known in the ocean. And there's a detail that changes everything when you think about the origin of life on Earth. Hydrothermal vents may have been the cradle of everything. The discovery of chemosynthetic ecosystems changed not just marine biology, but also discussions about the origin of life on Earth. Before 1977, the most widely accepted hypothesis about where life originated involved the primordial soup, a mixture of organic compounds in shallow oceans, warmed by ultraviolet light. Hydrothermal vents offered a radically different alternative. Hydrothermal chimneys provide exactly the kind of environment that many origin-of-life models consider favorable: temperature and pH gradients, concentration of reduced inorganic compounds, porous mineral surfaces that could have functioned as primitive membranes, and a continuous flow of chemical energy. One of the most unexpected ecosystems in the deep ocean isn't associated with any source of heat or chemical fluid, it's associated with wood. When tree trunks sink into the ocean and reach the bottom, they become centers of intense biological activity in an environment where any concentrated organic resource is extraordinarily valuable. A dead tree becomes a world. Organisms called xylotrophic bivalves, literally wood-eaters, bore into the wood and digest it with the help of symbiotic bacteria living in their tissues. These animals create channels and cavities in the wood that are then colonized by a succession of other organisms, creating a temporary micro-ecosystem that persists as long as the wood lasts, which can be decades in the cold ocean floor. The connection between these wood-based ecosystems and those based on hydrothermal vents or whale falls goes beyond analogy. Some species are shared between these environments. This led to the development of a fascinating model, that islands of concentrated organic resource, whether wood, whale bones, or hydrothermal chimneys, function as stepping stones in a dispersal network that connects isolated populations across the deep ocean. The mesopelagic zone, between 200 and 1,000 meters of depth, is the stage for one of the planet's greatest daily migrations, an event that happened simultaneously in every ocean in the world but remained almost unknown until the 20th century. Every day, at dusk, billions of organisms rise from the deep toward the surface to feed, and at dawn return to the depths. It's the ideal vertical migration. The organisms making this journey, copepods, euphorsiids, lanternfish, squid, and hundreds of other species, rise hundreds of meters in a matter of hours, taking advantage of darkness to feed on phytoplankton and zooplankton at the surface with less risk of predation. At dawn, they descend again to the darker depths, where they remain relatively protected during the hours of daylight. This movement has a consequence that goes far beyond individual biology. It functions as a carbon pump. When these organisms rise, they incorporate organic carbon from the surface into their tissues. When they descend, and when they defecate, die, or are preyed upon in the deep, that carbon is deposited in deeper layers, removing it from the atmosphere. The ideal vertical migration is estimated to transport between 1 and 5 billion tons of carbon per year into the ocean depths. What almost no one realizes is that there's a small, nearly invisible organism that has a disproportionate impact on the transport of carbon to the ocean floor. There's an organism in the deep ocean that, despite being relatively simple, has an ecological impact disproportionate to its size, Bathochordaeus, a species of appendicularian living in the mesopelagic zone. It builds around itself a transparent structure called a house, made of mucolisaccharides, which functions as a sophisticated feeding filter. This house can be up to 1 meter in diameter, even though the animal inside is only a few centimeters long. It consists of chambers with filters of different sizes that capture organic particles from the water as the animal pumps water through it. When the filters become clogged, the animal simply abandons the structure and builds a new one, which can happen several times a day. The discarded houses, called ghost houses, sink quickly because they're dense and relatively large. They carry with them the captured organic particles, including carbon, and descend at a much faster rate than individual marine snow particles. This mechanism, multiplied across enormous populations of appendicularians in every ocean, represents a significant contribution to carbon transport into the depths, only identified as quantitatively important in the last 2 decades. the total biomass of mesopelagic zone organisms was systematically underestimated for decades. The fishing nets used in the first oceanographic expeditions had meshes that let smaller organisms escape, and larger fish simply fled when they detected the nets. Estimates based on those methods pointed to a modest biomass. But the reality, as it turned out, was very different. With the development of high-resolution underwater acoustics, which measures the volume of organisms by how they reflect sound pulses, estimates were dramatically revised upward. More recent calculations suggest that the biomass of mesopelagic fish alone may be between 1 and 10 billion tons, which would make these little-known, small, bioluminescent fish the most abundant category of vertebrates on the planet in terms of total biomass. This revision has direct implications for models of the global carbon cycle. If there are far more organisms making the deal vertical migration than previously thought, then the transport of carbon into the deep by that mechanism is also much greater than earlier models estimated. The deep ocean may be sequestering carbon on a considerably larger scale than current climate projections account for. Reproduction in the deep ocean presents a challenge that doesn't exist in the same way in any other environment: finding a mate. In an immense, dark, three-dimensional space with very low population density, the chances of two individuals of the same species meeting at the right moment are statistically small. Evolution responded to this problem with solutions that seem extreme, but make precise sense within that logic. The male deep-sea anglerfish is one of the most cited examples in deep-sea biology, and for good reason. The male is drastically smaller than the female, in some species, up to 60 times lighter. When he finds a female, he bites her and doesn't let go. Over time, their tissues fuse, the circulatory systems connect, the male's organs progressively regress, and he essentially becomes a permanently attached reproductive appendage on the female's body. What makes this biologically remarkable isn't just the behavior itself, but the immunological mechanism that allows it. Normally, an organism's immune system would reject foreign tissue. It's the same principle that makes transplants difficult in human medicine. Deep-sea anglerfish have developed a specific immune suppression that allows this fusion without rejection. Understanding this mechanism has generated genuine interest in applied immunological research. This starts to get more interesting when you think of bioluminescence not just as light, but as language. Communication in the deep ocean, where light doesn't exist as a means of long-distance visual signaling, depends on other channels. Sound is one of them. But bioluminescence also functions as language. Different species have distinct flash patterns, frequency, duration, color, and the position of emitting organs vary in ways that allow species-specific recognition. Some deep-sea squid have photophores, light-producing organs, distributed across their bodies in patterns that appear to be species and sex-specific, suggesting that light functions as visual identity in an environment that is, paradoxically, completely dark. Each organism carries its own luminous signature, unique, recognizable, functional. There's also a particularly ingenious defensive use of bioluminescence, counterillumination. Many organisms in the mesopelagic zone have photophores on the ventral side of their bodies that emit light downward. The intensity of this light is regulated to match the light coming from above, creating a silhouette that disappears when viewed from below, because the animal's glow blends with the residual brightness of the surface. It's a form of active, dynamic camouflage, invisible and continuous. The vampire squid, whose scientific name, Vampirotuthis infernalis, literally means vampire squid from hell, occupies a unique position in the cephalopod evolutionary tree. It's neither squid nor octopus, but the only living representative of a separate order that diverged from both lineages hundreds of millions of years ago. It lives in the oxygen minimum zone, between 600 and 900 meters, where few predators can survive. Despite the name and intimidating appearance, with proportionally enormous eyes, black or reddish skin, and structures resembling capes between its tentacles, the vampire squid is remarkably peaceful. It doesn't actively hunt, it feeds mainly on marine snow, capturing organic particles with long, sticky filaments that extend from its body. It's one of the only known cephalopods to adopt this passive feeding strategy. When threatened, the vampire squid doesn't expel dark ink like other cephalopods, because ink would be invisible in the darkness of the abyss. Instead, it expels a cloud of bioluminescent mucus that glows for several minutes, confusing the predator while the animal escapes into the darkness. It's an adaptation that transformed bioluminescence from an attractant into a defensive weapon, an elegant inversion of the most common use of that ability. Deepwater coral is one of the most surprising discoveries in oceanography in recent decades, not for its existence alone, but for its scale. While tropical coral reefs are well known and widely studied, cold and deep water coral reefs remained almost unknown until the late 20th century. Today we know they are as extensive as tropical reefs, and possibly older. These corals live without sunlight and therefore without the symbiotic algae that provide energy to tropical corals. They capture food directly from the current, zooplankton and organic particles that pass within reach. They grow much more slowly than tropical corals, a few millimeters per year, which means deep coral reefs several meters tall are thousands of years old. The coral Lophelia petusa, the most common species in deep Atlantic reefs, has been found forming structures dating back more than 8,000 years. These reefs function as biodiversity hotspots in the deep, sheltering hundreds of species of fish, crustaceans, and invertebrates. At the same time, they're extraordinarily vulnerable. Bottom trawling can destroy in minutes structures that took millennia to form. The deep ocean is the stage for a geological phenomenon that connects the Earth's interior to the surface in unexpected ways: submarine volcanism. More than 70% of all the planet's volcanic activity occurs under the oceans, mainly along mid-ocean ridges. This continuous volcanism not only creates new oceanic crust, it releases gases into the water column and indirectly into the atmosphere. During geological periods of intense submarine volcanic activity, as happened several times throughout Earth's history, these emissions were sufficient to alter the composition of the atmosphere and significantly influence global climate. The ocean floor and the sky above are connected in ways we don't normally imagine. When larger eruptions occur at isolated underwater volcanoes, they can create temporary islands that eventually erode below sea level, or permanent islands like Hawaii. Hawaii is the visible top of a chain of submarine volcanoes created by the Pacific Plate moving over a fixed hotspot in the mantle, and most of that chain is completely submerged, invisible, forming a sequence of seamounts stretching for thousands of kilometers. And there's a detail that changes everything when you consider seamounts. These extinct volcanoes are oases of biodiversity in an oceanic desert. Seamounts, extinct or dormant volcanoes that rise from the ocean floor without reaching the surface, are one of the most biologically rich environments in the deep ocean, and at the same time one of the least studied. Estimates suggest there are between 30,000 and 100,000 seamounts taller than 1,000 meters in the world's oceans. Most have never been visited. What makes seamounts ecologically special is the way they interact with ocean currents. When a deep current encounters a seamount, it's forced upward, a process called localized upwelling, bringing nutrients from the deep into shallower, sunlit layers. This creates zones of high biological productivity directly above the seamounts, attracting fish, sharks, sea turtles, and cetaceans in concentrations far greater than in surrounding waters. The flanks of seamounts also function as islands of biodiversity in the deep, with rocky substrates that allow corals, sponges, and sessile invertebrates to anchor in environments where the bottom is normally just soft sediment. Many species found on specific seamounts exist only on that seamount, making them points of unique biodiversity on a global scale. And since bottom trawling frequently operates over them, the destruction of this biological heritage has been advancing faster than science can document it. One of the most dramatic phenomena on the ocean floor is submarine landslides, mass movements of sediment that can be orders of magnitude larger than any terrestrial landslide. The largest documented submarine landslide occurred about 8,000 years ago, off the coast of Norway, and is called the Storegga Slide. It moved approximately 3,500 cubic kilometers of sediment, a volume that would be enough to cover all of Great Britain with a layer of sediment more than 10 meters thick. This event generated a tsunami that struck the coasts of Scotland, Norway, and Iceland with waves estimated at more than 20 meters in height. All of that, triggered by the ocean floor. What worries modern geologists is that methane hydrate deposits on the seafloor may contribute to sediment instability. If the warming of deep waters dissolves the hydrates that function as cement within the sediments, this could destabilize slopes that currently appear safe, a mechanism that represents an unknown factor in tsunami risk models for coastal populations. The ocean floor holds something that completely defies intuition: rivers and lakes underwater. Not metaphorical rivers, real rivers, with beds, banks, currents, and even waterfalls that flow along the ocean floor like terrestrial river systems, but completely immersed in seawater. Rivers inside the ocean. These phenomena exist because water in certain seafloor regions can have significantly different density from the surrounding water due to temperature, salinity, or concentration of suspended sediment. Denser water sinks and flows along the bottom following the topography, exactly as a river follows the terrain on land. The largest waterfall on the planet, measured by water volume, is at the bottom of the ocean. The Denmark Strait Cataract, between Greenland and Iceland, is the point where cold, dense Arctic water plunges into the North Atlantic at depth, a drop of about 3,500 meters, with a water flow more than 2,000 times greater than the flow of Niagara Falls. It's completely invisible from the surface. No one has ever seen it with their own eyes. The ocean floor contains one of the most complete and well-preserved geological records on the planet, and scientists have learned to read it like an archive. The sediments that slowly accumulate in the abyss preserve information about climate, atmospheric composition, ocean temperature, and even cosmic events over tens of millions of years. Extracting this archive is done through sediment cores, cylinders of material removed from the seafloor by specialized equipment that can penetrate dozens of meters below the surface of the ocean bed. Each centimeter of that cylinder represents decades or centuries of deposition, and the chemical and biological analyses of the material reveal the environmental conditions of each period. It's a reading of the past written in silence. One of the most useful markers in these cores are foraminifera, unicellular organisms with calcareous shells that live in great numbers at the ocean's surface and sink when they die. The ratio of oxygen isotopes in foraminifera shells records the temperature of the water in which they lived with surprising precision. By analyzing these ratios along a core, scientists can reconstruct the temperature history of the oceans with a resolution of millennia, a thermometer of the past preserved in the silence of the abyss. What seems simple isn't, and the sediments of the deep ocean hold records of events that happened not only on Earth, but in the cosmos around it. One of the most dramatic events recorded in deep ocean sediments is the Cretaceous-Paleogene boundary, the geological layer that marks the mass extinction that wiped out non-avian dinosaurs 66 million years ago. This layer, identifiable in sediment cores from around the world, contains anomalous concentrations of iridium, an element rare in Earth's crust but abundant in asteroids. This iridium anomaly was the main evidence that led physicist Luis Alvarez and his geologist son Walter Alvarez to propose, in 1980, that the extinction was caused by an asteroid impact. The hypothesis was controversial at the time, but the subsequent discovery of the Chicxulub crater, partially submerged in the Gulf of Mexico, confirmed that an asteroid roughly 10 kilometers in diameter had collided with Earth in that period. What the sediment record of the ocean floor revealed about this event goes beyond confirming the impact. Cores taken from different points across the ocean show how the extinction spread, which groups disappeared first, how oceanic productivity collapsed, and how it took millions of years for marine ecosystems to reorganize. The abyss preserved the full account of one of the greatest biological catastrophes in Earth's history. The deep ocean has also preserved evidence of cosmic events with a fidelity that surprises even specialists. Beyond the Iridium anomaly, abyssal sediments contain microscopic spheres of glass and metal, generated by meteorite impacts and by the heating of cosmic dust as it enters the atmosphere. These particles are continuously deposited on the ocean floor, creating a record of impact activity over geological time. More recently, researchers found iron-60 grains on the floor of the Pacific, a radioactive isotope not naturally produced on Earth, but generated in supernovas. The distribution of these grains in sediment layers from 2 to 3 million years ago suggests that a supernova occurred relatively close to the solar system during that period. The deep ocean, in this sense, doesn't just record Earth's history, it records the history of the planet's cosmic surroundings. The ocean floor is, among other things, an archive of the universe. This starts to get more interesting when you realize that serious exploration of the deep ocean only began a few decades ago, and what we've found so far is a tiny fraction of what's out there. The history of deep ocean exploration begins long before modern submersibles. It begins with ropes and weights. The most primitive method of measuring ocean depth was simply lowering a rope with a weight until it touched the bottom and measuring the length of rope used. It was laborious, imprecise, and limited to relatively shallow depths, but it was the only method available for centuries. The HMS Challenger expedition, between 1872 and 1876, marked the first systematic attempt to understand the deep ocean as a scientific subject. The British ship travelled nearly 130,000 kilometres, collected sediment and water samples at hundreds of points, and catalogued thousands of new species. The equipment was rudimentary, but the data collected was enough to establish that the deep ocean was a biologically rich and geographically varied environment. What makes the Challenger expedition remarkable isn't just what it discovered, but what it established as a model. For the first time, a ship was equipped and operated explicitly for ocean science, with onboard laboratories, a dedicated scientific team, and a systematic collection protocol. The 50 volumes of reports published over the following 19 years formed the foundation of modern oceanography, and many of the species and phenomena they identified are still being studied today. On January 23, 1960, the bathyscaphe Trieste descended to Challenger Deep with Jack Pickard and U.S. Navy Lieutenant Don Walsh aboard. They reached 10,916 meters, remained on the bottom for about 20 minutes, and noticed something no one expected: a flat fish, apparently a flounder, resting on the sediment. The observation was controversial. Some scientists suggested it was a sea cucumber, not a fish, but regardless, it confirmed that multicellular life existed at the deepest point on the planet. After that 1960 descent, more than half a century passed before humans returned to Challenger Deep. The gap wasn't from lack of interest, but from lack of suitable vehicles. In March 2012, filmmaker James Cameron descended to Challenger Deep in the deep-sea Challenger submersible. Cameron spent about 3 hours on the bottom, collecting samples and images. What he found was described as a lunar landscape, vast, flat, covered in soft sediment, with far less visible life than popular images of the deep ocean suggested. But the sediment samples collected revealed, after laboratory analysis, a dense and diverse microbial community. The floor of Challenger Deep isn't biologically empty, it's inhabited by forms of life simply not visible to the naked eye, found at surprisingly high densities for such an extreme environment. Life, once again, was there. Remotely operated vehicles, ROVs, transformed deep ocean exploration more profoundly than any previous advance, simply because they eliminated the need to put human beings at risk. For ocean science, they open possibilities that were previously impractical. An expedition with a crewed submersible might spend only hours on the bottom per dive. An ROV can operate for continuous days, controlled in shifts by different operators. Most of the detailed knowledge that exists today about hydrothermal vents, seamounts, and abyssal communities was accumulated by ROVs over the past 3 decades. They're the ones transmitting the images that reach the surface, those creatures lit by white floodlights in the absolute dark, looking like they belong to another world. In a way, they do. And the current frontier of exploration isn't even ROVs anymore, it's autonomous underwater vehicles, AUVs, which operate independently, without a tether, following pre-programmed routes for hours or days, covering hundreds of kilometers and collecting data with sonar, cameras, and chemical sensors. The convergence of increasingly capable AUVs, artificial intelligence for real-time data analysis, and declining operational costs is making possible a scale of deep ocean exploration that wasn't imaginable a generation ago. What almost no one realizes is that the current that warms all of Europe has its origin on the ocean floor. There's a current in the deep ocean that doesn't appear on surface current maps, but is responsible for distributing heat, salt, oxygen, and nutrients across all the world's oceans on a timescale spanning centuries to millennia. It's called the thermohaline circulation, and it works like a global conveyor belt connecting all the oceans in a single circulatory system. The mechanism begins in polar regions, especially in the North Atlantic and around Antarctica. In these regions, surface cooling and the formation of sea ice cause water to sink in dense columns that plunge toward the ocean floor. This cold, dense water then flows along the bottom of the oceans toward tropical regions, where it gradually warms, rises, and returns to the surface to complete the cycle. The full journey of this circulation, from the point where water sinks in the North Atlantic to where it resurfaces in the Pacific or Indian Ocean, takes between 500 and 1,000 years. This means water currently sitting on the floor of the equatorial Pacific may have been at the surface of the North Atlantic during the Middle Ages. The thermohaline circulation isn't just an oceanographic phenomenon, it's a mechanism of climate memory that connects the past to the present on timescales that challenge intuition. The North Atlantic Current, part of the larger system called the AMOC, is responsible for a remarkable climate anomaly. Western Europe is significantly warmer than other regions at the same latitude. London is at the same latitude as Calgary, Canada, but has much milder winters. Oslo is farther north than most of inhabited Canada, but rarely sees temperatures as extreme as those on the Canadian prairies in winter. Without this current, climate models estimate that average temperatures in northwestern Europe could drop by 5 to 10 degrees Celsius. What concerns climatologists is that the AMOC has been showing signs of weakening. The melting of Greenland's glacier is injecting large volumes of fresh water into the North Atlantic, fresh water that is less dense than salt water and therefore doesn't sink as easily. Paleoclimate data drawn from ocean sediment cores show that the AMOC has collapsed abruptly in the past, with rapid and severe climate consequences for the Northern Hemisphere. That this kind of abrupt change is possible, and that the mechanism causing it is happening again through Greenland's melting, is one of the reasons why monitoring the AMOC is considered a pressing scientific priority. The deep ocean is the planet's largest carbon reservoir, larger than the atmosphere, larger than all terrestrial vegetation combined, larger than all soils. The carbon dissolved in deep waters represents approximately 37 trillion tons, about 50 times more than exists in the atmosphere as co. Understanding how this carbon enters, remains, and eventually leaves the deep ocean is central to any model of the global carbon cycle. Carbon reaches the deep ocean through multiple pathways. The physical pump, the dissolution of atmospheric CO into cold surface water, which then sinks, contributes one portion. The biological pump, the sinking of organic matter produced by photosynthetic surface organisms, contributes another. And the carbonate pump, the sinking of calcareous shells from marine organisms, adds inorganic carbon to the bottom. Once in the deep ocean, this carbon can remain sequestered for centuries or millennia. Carbon that enters the deep circulation in the North Atlantic may not return to the surface, and therefore to the atmosphere, for 1,000 years or more. This means the deep ocean doesn't just store carbon, it removes it from the active climate cycle for periods that are long in human terms, though short in geological ones. The abyss is, among other things, a time vault. And this is where things get strange. The oxygen you're breathing right now has a direct connection to the ocean floor. The interaction between the deep ocean and the creation of atmospheric oxygen is a story that begins billions of years ago and continues today. Today, it's estimated that between 50 and 80% of the oxygen produced by photosynthesis on the planet comes from ocean phytoplankton, microscopic organisms that live in the sunlit layer of the ocean. What connects this to the deep ocean is that phytoplankton productivity depends directly on nutrients that rise from the depths. Nitrogen, phosphorus, iron, and silicon, the elements phytoplankton needs to grow, accumulate in deep waters through the decomposition of organic matter that sinks. When these nutrients are brought to the surface by upwelling or by thermohaline circulation, they fuel the growth of the phytoplankton that produces the oxygen we breathe. In a very direct sense, therefore, the oxygen in every human breath has a connection to processes occurring in the ocean depths. Disruptions that reduce the efficiency of deep circulation have the potential to reduce phytoplankton productivity, which would affect both oxygen production and the ocean's capacity to absorb atmospheric carbon. It's a chain of dependencies that connects the abyss to the atmosphere in ways most people never imagined. In 1997, military hydrophones positioned in the Pacific Ocean picked up an extraordinarily intense low-frequency sound, so intense it was detected by sensors more than 5,000 kilometers apart. The sound lasted approximately 1 minute, had characteristics consistent with a biological origin, and didn't match any known vocalization from whales or any other catalogued animal. The NOAA researchers who analyzed it gave it a name that stuck: the bloop. The bloop generated considerable speculation for years, including, inevitably, theories about unknown giant sea creatures. Subsequent scientific analysis reached a more mundane but equally fascinating conclusion: the sound is consistent with noise produced by large masses of ice fragmenting in Antarctica, a phenomenon called icequake, where ice under pressure releases energy suddenly and produces low-frequency acoustic signals that the SOFAR channel can propagate over intercontinental distances. The bloop case illustrates something important about the deep ocean as an acoustic environment. It amplifies and carries sounds from diverse origins in ways that can make the unusual seem inexplicable before careful analysis. Since the installation of military hydrophone networks after World War II, dozens of anomalous sounds have been recorded and catalogued, some explained, others still under analysis. The deep ocean continues to be, in acoustic terms, an environment that holds surprises. The Hadal Zone, ocean trenches below 6,000 meters, is the least explored environment on the planet, and every expedition that reaches it returns with discoveries that redefine what was expected to be found there. One of the most unsettling was the detection of industrial contaminants in organisms living at the deepest point in the ocean, at more than 10,000 meters of depth, completely isolated from any direct source of human pollution. In 2017, researchers analyzed amphipods collected from the Mariana Trench and the Kermadec Trench and found concentrations of PCBs, polychlorinated biphenyls, industrial compounds banned in most countries since the 1970s, that were 50 times higher than those found in crabs from heavily polluted rivers in China. The presence of these compounds in the deepest animal in the ocean, at those concentrations, was a discovery that surprised even the most experienced researchers in the field. This discovery demonstrated unequivocally that no part of the ocean is remote or deep enough to be isolated from human impact, a conclusion with direct implications for ocean management policies. The abyss carries our marks, even without ever having seen us. What almost no one realizes is that the plastic we throw away can take decades to reach the deepest point on the planet, but it gets there. Plastic has reached the ocean floor. Microplastics, fragments smaller than 5 mm, have been found in sediments of abyssal plains across all oceans, including in the deepest trenches on the planet. The Mariana Trench was found to have concentrations of microplastics in its sediments comparable to those in some of the most polluted coastal regions in the world. The explanation lies in the sinking mechanism. Plastics at the surface are colonized by bacterial biofilms that increase their density, then ingested by zooplankton, packaged in dense fecal pellets, and rapidly transported to the bottom. Ocean trenches, due to their funnel-shaped topography, concentrate material that sinks from the surrounding area, functioning as traps for sediments and, consequently, for contaminants. What isn't yet fully understood is the impact of these microplastics on abyssal ecosystems. Deep-sea organisms that ingest sediment involuntarily incorporate microplastics into their tissues. The physical and chemical effects of this ingestion on organisms adapted to an environment that, until the industrial era, contained no synthetic polymers, are only beginning to be systematically investigated. There's a category of organisms in the deep ocean that deserves special attention for its implications for medicine: sponges. Sponges are primitive animals, no nervous system, no organs, essentially biological filters, but they produce an extraordinary variety of chemical compounds that don't exist anywhere else in nature. This chemical production has a defensive function. Sponges can't move to escape predators, so they depend on chemical toxicity to protect themselves. Over hundreds of millions of years of evolution in this defensive mode, they developed molecules with structures that human organic chemists would never have synthesized, and some of these molecules have remarkable pharmacological properties. Compounds derived from deep-sea sponges are at the foundation of drugs for certain types of cancer, antivirals, and immunosuppressants that are used clinically today. The vast majority of deep-water sponge species have never been chemically analyzed. The chemical biodiversity of the deep ocean represents a pharmacological library of unknown dimensions that humanity is still learning to read. Every new species discovered is a page not yet opened in that library. Giant squid, Architeuthis ducks, are perhaps the most mythologized animals of the deep ocean, and for good reason. They grow to more than 13 meters in length, have the largest eyes in the animal kingdom, which can reach 30 centimeters in diameter, and live at depths between 300 and 1,000 meters in every ocean in the world. Despite all that, the first photographic record of a live giant squid in its natural habitat was obtained only in 2004 by Japanese researchers using a baited camera at 900 meters of depth. The size of the giant squid's eyes is an adaptation to detect bioluminescence from predators in the semi-lit depths where they live. The giant squid's main predator is the sperm whale, and the most widely accepted hypothesis is that eyes that large allow them to detect the faint bioluminescence produced when a sperm whale disturbs bioluminescent organisms as it swims, an involuntary luminous signature that gives away the predator's presence at distances that smaller eyes couldn't detect. The relationship between sperm whales and giant squid is one of the most documented in the deep ocean, indirectly. Sperm whales caught by historical whalers frequently had circular scars produced by the toothed suckers of giant squid, and whole or partial giant squid were found in sperm whale stomachs. For decades, this indirect evidence was the primary source of information about these extraordinary animals, which remain, despite technological advances, extraordinarily difficult to observe in their natural environment. The question of how much of the deep ocean has been explored has an answer that depends on what you consider exploration, but any reasonable definition produces a percentage that is disturbingly small. If the criterion is a direct visit by a vehicle with observation and collection capability, the fraction of the ocean floor that has been examined in detail is estimated at less than 0.001%, an area equivalent to a few small countries, in a territory larger than all continents combined. This means that every expedition into the deep ocean, regardless of where it goes, has a high probability of finding something that has never been seen before. Not occasionally, systematically. Recent expeditions to unmapped seamounts return with new species rates of 50% or more among the organisms collected. Regions of the Hadal Zone that received their first visit in recent years revealed complete communities of organisms that science didn't know existed. We live in an era when satellites have mapped the surfaces of planets billions of kilometers away with meter-level resolution, and yet the floor of our own planet remains largely unseen, unsampled, and not understood. The deep ocean isn't just Earth's largest biome, it's the greatest scientific frontier that still exists on this planet. One of the most open questions in deep-sea biology is about what hasn't yet been seen, and there are reasons to believe that large, still uncatalogued animals may exist in the deep. Not necessarily mythical monsters, but organisms of significant size that simply have never been encountered because exploration coverage is so sparse. The most recent example supporting this possibility is the colossal squid, Mesonychoteuthis hamiltoni, whose adults can reach 14 meters and weigh more than 700 kilograms, making it the heaviest invertebrate on the planet. Despite that extraordinary size, the first complete adult specimen was accidentally caught by fishermen only in 2007. Before that, the species was known mainly from fragments found in sperm whale stomachs. If an animal of that scale could remain essentially unknown until the early 21st century, it's reasonable to imagine that other organisms of comparable size might exist in regions of the deep ocean that have never received direct exploration. The deep ocean remains the most likely place on Earth where a truly surprising zoological discovery could happen at any moment. And there's a detail that changes everything when you think about the future of the deep ocean. For the first time in history, there's a species capable of knowing it and deciding its fate. The deep ocean began to exist, in its current configuration, about 200 million years ago, when the supercontinent Pangaea began to fragment and the modern oceans gradually took shape. In that span of time, it survived 5 mass extinctions, multiple glaciations, anoxic events that turned vast regions into dead zones, asteroid impacts, and continental-scale volcanic eruptions. Life in the deep adapted, reorganized, and persisted through disturbances that eliminated most of the species that existed at the surface. What is happening now? Warming, acidification, expansion of hypoxic zones, contamination by plastics and industrial compounds, pressure from mining, is different from previous disturbances in one specific way: speed. The mass extinctions of the past occurred over timescales of thousands to millions of years, allowing time for gradual adaptation and recolonization. The changes happening today are occurring over decades, faster than most long-lived, slow-reproducing deep ocean organisms can respond evolutionarily. But there's also something different in a positive sense. For the first time in the history of the deep ocean, there is a species with the ability to know it, understand it, and make decisions about its future. The technologies being developed now, autonomous vehicles, permanent observatories, environmental genomic analysis, artificial intelligence applied to marine biology, have the potential to transform knowledge of the abyss more rapidly in the coming decades than in all previous centuries of exploration combined. What's missing, more than technology, is the collective decision to use that knowledge to protect what still exists, before discoveries and losses become indistinguishable. The abyss has been waiting for us for 200 million years. Perhaps it's our turn to wait for it, to approach slowly, with care, with the humility of those who know they are entering a world they don't yet understand. There's something deeply calming in the fact that the planet's largest environment is still, for the most part, unknown. That somewhere beneath all the world's waters, life quietly keeps doing what it has always done, adapting, persisting, glowing in the dark. Without waiting to be discovered. Without needing us to exist. And at the same time, every time a submersible descends, every time a camera sends back images from the bottom, every time a scientist analyzes a sediment core, something changes. The abyss becomes a little less unknown. A little more present in our awareness. A little more protected, perhaps, by the simple act of being seen. It's a story still being written, in the sediments of the floor, in the genetic sequences of nameless creatures, in the data from sensors measuring the temperature of waters no one has ever seen. A slow, patient, immense story. And we, with our instruments and our questions, have only just begun to read the first pages. And as you drift into a deep and restful sleep, remember to subscribe so these stories can keep finding you night after night. Sleep well, and sweet dreams.